So, welcome to the second series of lectures on functional analysis. So, for the first part, we will discuss the seminorm and norm spaces. So, let's start with the definition of a seminorm. So, here, let us consider a vector space X over the field K. So, here, the field K is either the set or the field of real numbers R or the field of complex numbers C. So a function p from x to r will be called a seminorm on the vector space X if we have the following properties: n1, homogeneity, and n2, the triangle inequality. Uh, n1 tells us that p of alpha x is the same as the magnitude of alpha times p of x for any pair of scalar and vector x. So if you think of this equation, well, you can imagine this as a scaling property. Here, this is the scaled vector. So depending on the value of alpha, so if the magnitude of alpha is greater than 1, that vector will be elongated, and it will be shortened if the magnitude of alpha is less than 1. So taking the seminorm of the scaled vector is the same as multiplying the magnitude of the scaling factor, it's the absolute value of alpha, and multiply it with the seminorm of x. Okay. So for a real number alpha, the absolute value will be your usual absolute value. And in the case of complex numbers, this will be the magnitude of a complex number. Second, we have the triangle inequality. So the seminorm of the sum is less than or equal to the sum of the seminorms. So if you think of, let's say, the seminorm as a length, for instance, then this means that if you have two vectors, x and y, then the sum, which is the diagonal of the determined parallelogram, so suppose this is x, this is y, you create the parallelogram corresponding those two vectors, and you could translate, and this is the same as x. So here that the length of the side x plus y is less than the sum of the lengths. So that's the place where this inequality was termed on. Okay? Kaya siya tinawag na triangle inequality. So as usual, the pair xp, where x is a k vector space and p is a seminorm on x, then this pair will be called a seminorm. And if, again, the seminorm p is clear in the context, we instead refer to x as the seminorm for simplicity. Okay. First property is that the seminorm of the zero vector is the zero scalar. So you should not be confused here. There are two zeros, but of course, one should see them in the appropriate context. So the argument of p should be in x. So this first zero here on the left-hand side would be the zero vector of x. On the other hand, the right-hand side is a real number because p, the output of p is a real number. Well, to say this, we just need to write, okay, the vector p as the scalar times the zero vector in the x. And then if you apply homogeneity, so that's n1, you pull out the absolute value of the scalar 0 and then evaluate 0. Take note that this is the left-hand side is p of 0, zero vector, and any real number multiplied by 0 would be 0. So that would be justification of this first property. Okay, so the seminorm of the zero vector is 0. We also have the so-called reverse triangle inequality, which states that the magnitude of the difference between the seminorms is less than or equal to the seminorm of the difference. So let us look at the proof. So let's start with the p of x and write this as p of x minus y plus y. So we just add 0, and this 0 is y minus y. And this is one of the common or old tricks in analysis, adding 0. Okay, so from nothing, we will get something. Okay, so here we will apply the triangle inequality. So that should be n2. So the seminorm of the sum is less than or equal to the sum of the seminorms. Okay. And this implies that after subtracting p of y both sides, and we get this estimate. Now, you just, let's say, interchange the roles of x and y. You end up with the following. So p of y minus p of x is less than or equal to p of y minus x. Okay, here we can write this as p of -1 times x minus y. And if you apply the homogeneity, okay, this one here is equal to p of x minus y. So that is n1, okay? And from these inequalities, let's say this is inequality 1 and inequality 2. So inequality 1 and inequality 2 implies the reverse triangle inequality. Okay. And from this, in fact, we could see that the seminorm is non-negative for any x in the vector space. Well, to see this, in the reverse triangle inequality, you just take y to be 0, so that you will have the following. So x minus 0, that's x. So this is greater than or equal to the absolute value of p of x minus p of 0. Okay. And we know that this is 0. So a number that is greater than its absolute value must be non-negative. Or in other words, we know that the absolute value is always non-negative. Hence, the seminorm of any vector would be non-negative. Okay. Here, there's no reason that if p of x is equal to 0, then x is equal to 0. However, if the function satisfies that property, then we say that it is a norm. So what is a norm? This function, okay, double bar, is called a norm on x if it satisfies n1 and n2. So in other words, it's a seminorm, and that if the value with respect to a vector x is 0, then that must be the 0 vector. Okay. So if you have, if you imagine this, or if you take this as the Euclidean norm, then this is one that we could expect. And in the same way as we have already done, if you have a pair X and a norm on the vector space X, then we call the pair a norm space. And as usual, if the norm is clear in the context, we shall refer X as the vector space. Okay. Sometimes we will write the norm with a subscript. Okay. So a subscript means that would be the norm corresponding to that space. Well, this will be useful later if we are dealing with several norm spaces. So as an example, so for p greater than or equal to 1 and less than or equal to infinity, we consider the so-called little LP spaces. Okay. And I think I'll use the exponent notation. Okay. So this is the set of all sequences in the field K, either the real numbers or the complex numbers, having a finite P norm. Okay, so the little LP norm is defined as follows. So if P is finite and it's greater than or equal to 1, what you do is you take the magnitude of the components, you raise that to the power of P, take the sum, and then raise that to 1 over P. Okay, so this is the infinite version of your Euclidean norm if P is equal to 2, of course. Now, if P is infinity, then we just define the little L infinity norm of a sequence to be the largest magnitude of the terms. And this little LP, the space of sequences having a finite P norm, is a Banach space. Okay. So one can prove this, but for now we skip the proof because we will prove this later in a more general setting when we discuss measure spaces, because one can view this infinite series here, let's say, as a Lebesgue integral with respect to the counting measure. So we defer the proof when we go to the measure theory portion. So let's say measure theoretic proof in the future discussions. Okay. Here we have an example of a semi-norm, but not a norm. Okay. So P sub I, you can think of this as the projection onto the ith axis, let's say. So P sub I of x is equal to the absolute value or magnitude of the ith component. So here's an illustration of the case in the two-dimensional Euclidean space. So if you have x having components x1 and x2, so P sub 1 would be the projection with respect to the x-axis. And then you take the magnitude, of course, or the absolute value. Here, it is now positive, so we don't need to take the absolute value. But okay. Since the projections are positive, then you have that. Okay, and similarly, the projection with respect to the second coordinate would be the projection with respect to the x-axis, and then you take the magnitude. Okay, the fact that this is a seminorm follows from what? The properties of the absolute value. Okay, the triangle inequality is satisfied by the absolute value. Hence, a P sub I satisfies also the triangle inequality. Homogeneity of P sub I follows from the fact that the absolute value of the product of two numbers would be the product of the absolute values. So indeed, P sub I is a seminorm. Well, this is not a norm. For instance, you could see that the kernel of P sub I, well, this is not a linear, so let's just say the null set of P sub I. So P of x sub I is equal to 0 if and only if x is an element of the following OR. I can write this as, let's say, x sub 1, x sub I minus 1, and then the ith component is 0. Okay. Oops, I apologize for that. Let's go back to the. Okay. So you can have a seminorm that it is not a norm. Here, n, of course, is taken to be greater than or equal to 2, of course. Okay. So if, for instance, in this illustration here, if you are on, let us consider, let's say, P sub 1, okay? The projection would be 0 if you are located on the y, on the x-axis, okay? And or if you are located on the y-axis, okay? So if you project any point on the y-axis here, the projection would be 0. But those vectors are non-zero. Okay. So this is a seminorm, but not a norm. Okay. Now, from a seminorm, how do we create a norm? So this is similar to what we have discussed in the case of metric spaces. So you consider an equivalence relation. So two vectors are related if and only if the seminorm of the difference is 0. One can show that this satisfies the axioms or the properties of being an equivalence relation. And that is, it is reflexive. Well, it follows from the fact that the seminorm of the 0 vector is 0. This relation is also symmetric. This follows from the homogeneity of the seminorm. And finally, this satisfies the transitivity property since the seminorm satisfies the triangle inequality. Having this equivalence relation, we could create the factor quotient space x modulo tilde. This is the set of all equivalence clauses determined by the equivalence relation. And we define this a function as follows. So we define the norm of an equivalence class to be the seminorm of the representative. Of course, among other things, one should verify that this is well defined. In other words, this definition should be independent uh, with respect to the chosen representative for the equivalence class. And indeed, this is in fact a norm on the quotient or factor space. Okay, so we will not go into the proof because this is somehow the proof is identical with the case of what we did in the metric spaces. Okay, so from a semi-norm space, you could have you could create a norm space, but with respect to the factor space. So here, what you basically do is you collapse or you collect all vectors, excuse me, that have a map that have semi-norms 0. Okay, so you collect all of those and then you treat that as the 0 vector of your quotient or factor space. In the introduction, we've mentioned that one can generate a metric from a length. And this length here is the case of the norm. So if you have a norm space or a norm, one can define a metric. And this metric is defined as the norm of the difference. Okay. The definiteness of D follows from that of the semi-norm. The symmetry will follow from the homogeneity of the norm. And then finally, the triangle inequality is satisfied since the same property is satisfied by the norm. Okay, so you can immediately show that this is indeed a norm. Well, the additional property that we have is the translation invariance of this metric. Okay, so let's say you have a vector x and y. Okay, so x minus y would be this vector. Okay, now if you translate this, so just copy this one and paste it here. So if we translate this vector, okay, so this is now x minus z, y minus z. Okay, so we have translated the vector. Then this difference would be what? X minus z minus y minus z. Okay, so you can see here that the z would cancel, and you still have the same difference in fact. Okay, so the distance between 2 points, there's a typo here. There should be the distance between x and y. Okay, so if you translate the two vectors, the distance would be the same. And that is what we call translation invariance. Okay, so we take note that we cannot do this in a general metric space because unless you have a vector space structure. Here we have a vector space structure. So you can add vectors, you can multiply by scalar, and in particular, you can take the difference of two vectors. So to talk about translation invariance, you need to consider what? Let's say a vector space structure, for instance, of the space. Okay, so what is the complete version of a norm space? See, so a norm space which is complete with respect to the induced norm, okay, or induced metric, I should say, is called a Banach space. Okay. Again, so if you have a norm space, You have a norm, you have an induced metric. Okay. And with respect to this metric, if the space is complete, in other words, every Cauchy sequences converge to an element or converges to an element in the space, then it is said to be complete. And then that is a Banach space. So in short, a Banach space is a complete norm space. So a closed subspace of a Banach space is also a Banach space. Okay. Well, this follows immediately from the previous theorem that we have shown, that a closed subspace of a metric of a complete metric space is complete. Okay. So a closed subspace of a Banach space is also a complete metric space, and it has a norm. And what is the norm? Here, the norm is taken with respect to the original Banach space. Okay, so this theorem follows immediately from the one that we have shown in the situation of metric spaces. So of course, a classical example is the Euclidean norm, okay, Kn. So Kn here is the set of all n tuples of scalars in K, which is again either the reals or the complex numbers. So we have mentioned a while ago that this LP here, okay, is a normal space. So in fact, one can show that this is also a Banach space. So the set of sequences having a finite P norm is also complete. Again, we defer the proof when we go to the measure theory and Lebesgue integration theory lecture. Okay. However, there's an alternative proof, and it uses the Cantor argument, or what might be well known is the Cantor diagonalization argument. And again, as I said, you could look at the proof in the standard functional analysis textbook, but for the sake of time, we will not prove this because we will prove a general version later. An example of a norm space that is not complete is the following. So denote by C AB to be the set of all functions on the closed interval AB to R. Okay. And C here means that F is continuous. Okay. So this is just the set of all continuous functions on the closed interval AB. Let us define the norm. Okay. Of f as the integral of the absolute value of f. So what is the geometrical interpretation of this? Well, you could say that, let's say you have a function from A to B. So let's say this is A, this is B. It can have a negative part. Then you, let's say, project that one, and then you take the area under this two curve. Okay. Or you, I should say, you take the reflection with respect to the x-axis. So that would be the interpretation of this norm here. Okay. So again, let's do that here. So take a function f on a closed interval AB. So you project the or you reflect the negative part with respect to the x-axis, and then you take the corresponding area under the curve. So that would be approximately this part here. Okay. This is not a Banach space. Why? I'll give you an example of a Cauchy sequence that will not converge. Okay, to the to that space. Let's consider the sequence of functions. Okay. So this is Cauchy in the space, but it is not convergent. Okay. And let's take for simplicity that the interval, closed interval, is 0 to 1. Of course, the general case can be done via a linear transformation. In other words, you take the transformation of the closed interval AB to 0 to 1, either by expansion, contraction, or via translation. Okay, well, to visualize, at least to have an explanation, a rough explanation on why this is the case. So what would be the graph of these functions? Okay, so f1 would be this linear function. Okay, so that would be f1. f2 would be the quadratic function. f2. f3 would be the cubic, etc. So here, you will note that the graph will be going down. It's the same, okay, as if we are stretching. So think of this portion here, this red part, okay. If you push this towards the say the point 1. Okay. Take note that for each n, okay, the value is fixed at 1 because 1 raised to n for any n is always 1. So looking at this figure, it seems that the candidate limit, okay, would be this function. Okay. Of course, x sub n, if n is less than 1, x sub n tends to 0 as n tends to infinity. Okay, so this is what a geometric sequence, okay, having what a base that is less than 1. Now, if x is equal to 1, we know that xn is equal to 1 for all n. Okay, so that would be also the limit, right? So everywhere else on the closed interval 0, 1, the candidate limit seems to be this function. So 0 except on the value 1, and at 1 the value is equal to 1. So take note here that the candidate limit is not continuous. So that's why this space of continuous functions with respect to this norm, the integral of the absolute value, would not be complete. Okay, so that is the idea of this example here. So you could verify that this is indeed a Cauchy sequence. Okay. Okay, the same. How do I show this? The same business as with the metric spaces. Okay. What if I have a norm space that is not complete? Can I embed that into a complete a complete norm space? Well, this theorem is the analog of the theorem in the case of metric spaces that we have established in the last lecture. So given a norm space X, you can find a norm space X bar. Okay, that is complete. So we now call this a Banach space. So X bar with the what? With the following norm and a linear map from X to X bar in such a way that J is an isometry. Okay, so J of X, the norm of the image is the image of the, or the norm of the pre-image. And this Jx is dense in X bar. Okay. The question is, why is this an isometry or a distance preserving? Take note here that unlike in the case of general metric spaces where you don't have a vector space structure, a norm space has a vector space structure. So we want that the algebraic properties, in other words, the sum and the sum of two vectors and the scalar product of a scalar and a vector, those operations must be preserved. And that is precisely done by a linear map. Okay. Well, to say that this is indeed an isometry, if you look at the, let's say, the distance between the two images, okay, take note that the distance induced by a semi-norm is just by a norm is just the norm of the difference. Okay. So this is the distance between the two images. Now, as I say, J is a linear map, so the one inside the norm should be J, the image of the difference. So again, the difference of the images is the image of the difference. And if you apply the this equation here with X replaced by the difference, you will have. Okay, and this is basically the distance between X and Y. Okay, so in the case of a norm space, an isometry is a norm preserving function. And if you have a norm preserving function, then the with respect to the induced metrics, it is also an isometry in the sense that it is a distance preserving function. Okay, I will not give a complete proof. I'll just present you the main idea. So you follow the same construction. So you take equivalence clauses, okay? And in this case, you take, let's say, the limit. How should I define the norm of an equivalence clause? So this is what the norm of the equivalence class containing the Cauchy sequence x sub n. Okay. You define this as the limit as n goes to infinity of the norms of the x sub n's. Okay. So you follow the same equivalence relation. Here, xn is related to yn. So two Cauchy sequences are related if and only if the distance between the corresponding terms tends to 0. But since we are in the case of norm spaces, one can formulate that as the norm of the difference of the terms. So this is the corresponding equivalence relation, and your x would be still your factor space. So x bar would be your factor space. Okay. What is the map J? J would be the same as in the case of the metric spaces. Okay, so I will not go into the details, but again, as I said, you could follow the discussion in the case of metric spaces. And that's it for norm and semi-norm spaces. In the next part of this lecture, we will consider inner product spaces.